All right, so today the plan is to go over midterm exam questions quickly. If you have any questions, I'll be happy to answer them. And I will go over the solutions quickly and spending most time on the solution to the first question. The solutions to the other questions are straightforward, but the first one, which is the plane sweep algorithm, is I think it was one of the most difficult questions in the midterm exam. So I will detail the solution for question 1 of the midterm, which is here. And then I will go over quickly the solution sketches for the following questions. And then we are going to talk about Voronoi diagrams today. And we are going to see another plane sweep algorithm due to Steve Fortune for computing the Voronoi diagram for a given set of points. So our input will be again a set of points on the 2D plane, and we will create what is known as Voronoi diagram, which will be a subdivision of the plane that will associate areas to these input points, which are also called sites. And these areas will indicate the locus of points which are closest to that site. The problem is also called the post office problem. But yeah, Voronoi diagrams are very common popular structures in computational geometry. So today we'll see how to construct Voronoi diagrams. All right, so let's start with the midterm exam questions. I try to ask one question from every chapter. Some of them are very small questions, short questions. Some of them were a little bit longer. The first question was about the plane sweep technique that we have learned in chapter 2. Although another solution is also possible, because here I say, given ON log n algorithm that reports each point. Since I didn't say give a worst case ON log n algorithm, a trapezoidal map solution is also possible, which has an expected ON log n complexity for all the m points. With expected log n time, we'll be able to query each of the points. I mean, we could build a trapezoidal map of those triangles, and it will give you an expected ON log n time. Actually, I wasn't careful about wording the answer. I wasn't looking for a trapezoidal map solution, so I should have said here a worst case ON log n algorithm. But yeah, I think there was only one solution that used trapezoidal maps which got full credit because that's also an ON log n algorithm. It says expected ON log n running time. But I'm going to go over the plane sweep solution for this. There are a couple of critical points. I'm going to talk about those. And then, and then I'm going to proceed to the other questions, and I can take your questions as well. So, and this was one of the questions, the question that many of you lost some points. So in general, so I graded all of your midterm exam papers in section 1. So quite many of you lost like 7 points from here. Because the study structure, you did not detail how you query the study structure in log n time. Just for example, you say, check the point against the triangles in the study structure. The study structure at a given time may contain linear ON triangles, which will lead to an ON square algorithm. So, I mean, you may have indicated, you may have thought that you're going to use the study structure to make efficient queries, but if you don't write that in detail in your solution, that still a cause for losing points. All right. When I say, for example, this is not clearly written, you may object to that saying, oh, I meant this, meaning that is not a good objection. You have to, because I'm not grading your thoughts, whether you know it or not. I'm grading what you have written on your solution. So if the solution is not clear, that may be a cause for losing points. Okay, but anyway, everybody got very good points from the exam. The average probably is above 80. So yeah, thanks for submitting really nice papers. All of you all, submitted really good solutions. So let's get back to this problem. I'm going to talk about this in GIMP. So we have triangles. There may be some small triangles inside large triangles. Okay, and we have some points. Some of them are inside triangles, some of them are outside, and our goal is to report the points that are outside the triangle. That was the question. So here in this plain sweep algorithm, the event queue is one of the components, and the event queue is composed of points and the triangles vertices. So we have a total of 4n points, 3n coming from the vertices of the triangles, and we have n points which are given to us in queries. So if P is the set of points and T is the set of triangles, n points coming from here, 3n points coming from here. So we have a static event queue composed of 4n points, and we enter the points into the event queue based on their y coordinates. If they have the same y coordinate, we process the one with the smaller x coordinate first. So this is how the event queue is formed. And the sweep line moves downwards, and we have a study structure. Let's call it this T. And the study structure holds the triangle edges that currently intersect with it. All right, so we have these triangle edges, as you can see, and they can be ordered left to right. We can have a balanced binary search tree for the triangle edges that intersect this. And since the triangle edges do not intersect with themselves, the triangles are disjoint as given in the question, there will be a total order among triangle edges from left to right. And this order will not change at intermediate intervals. So what I mean is that if you just insert a triangle edge at its top vertex and you delete it when you come to its bottom vertex, an edge, and between this, its order among the other triangle edges will not change. So the balanced binary search tree will remain as is. And the way we insert them as edges, not as a single point with an x coordinate. So since it will be stored in the balanced binary tree as an edge, the query we make, for example, for a point, whether that point is to the left or to the right, will be compared against the edge, not the x coordinate, top x coordinate or this. So we have dynamic x coordinates, and we don't, since the order doesn't change, we don't need to update them continuously. So that's the idea. Now here, the critical thing is that as we move downwards for a point P, when we're handling, so the way we handle triangle edges, the way we handle these vertices is that when you come to a beginning vertex, you add the corresponding triangle edges. When you come to an end vertex of a triangle, you remove the triangle edges because the status, the sweep line stops intersecting them. So that's how we handle them. We are going to handle the top vertices of triangle edges with some detail. There are a couple of alternative solutions at this stage, but here the important thing is when we handle a point P, which is an element of this set, how do we make use of the study structure? So when you say, for example, find all the triangle edges to the left of this, find all of them to the, if any solution that tries to process the entire study structure will have an O(n) square worst case complexity. So we don't want to, so inserting these edges, deleting edges, they all take log n time in a balanced tree. And when we're processing, when we're handling a point like this, again, we cannot spend more than log n time. So this is what we need to have at most in order to achieve an n log n time overall, because there are n points, and for each, when processing a single point, we cannot spend more than log n time. So what we can do is, for example, things like give me the immediate left. You can make queries like, what is the immediate left edge of this point? What is the immediate right edge that is to the right of this point P? These queries, each of these queries take log n time. In senses, there are two of them, or a constant number of immediate left, immediate right of them. We can take a look at these two. For example, if these two belong to different triangles, then P is outside. We can say that. But this rule that I just said will not be correct for the cases where a small triangle is inside a large triangle, right? For example, if a point is here, when I'm processing it, this edge and this edge, they belong to different triangles, and therefore this is going to be reported as outside, but actually it's inside. You can also do this, get this, okay, this will be a problem for these triangles, then why don't I do this? I get the immediate left, maybe I put a pointer to the triangle, because this is a triangle's edge, I can have a pointer to the actual triangle, and do an intersection test for a point and a triangle, which is actually all one time. So I do an intersection test for the triangle that belongs to this edge, I do an intersection test that belongs to the triangle of this edge. So both of them are return P is outside, then P is outside. Okay, if any one of them returns P is inside, then it will be. So this is also possible. Okay, instead of just looking at triangle IDs, we can do intersection tests for these two triangles only. It will still be log n. But it's also possible to get rid of the problem of, I mean, we can still solve the problem by just looking at the triangle IDs, by actually not inserting triangles if they're inside a larger triangle. For example, I don't want to insert these triangles to the study structure. If there was something else here, I don't want to insert the triangle edges of this one. And how can I achieve this? Actually, if you look at the problem, it's not very difficult. What it will happen is that when you're processing, handling the top vertex of a triangle, you ask the same query as you did for a regular point P. You just ask that, is this top vertex of the triangle between, is it inside some triangle? So you get its left neighbor, immediate right neighbor. If they belong to the same triangle, then this vertex is inside a triangle, and then in that case, ignore this small triangle. Don't add it to the study structure. If these smaller triangles are not inserted into the study structure, then we will actually get rid of this problem of these cases where two neighbors are from different triangles and the point is inside. Actually, in our case, we will, if we do ignore these smaller triangles, we will be able to answer the query saying that, okay, if the left and right immediate edges belong to different triangles, then P must be outside. Okay, the critical thing here is this, using the study structure, either you say get the immediate left neighbor, right neighbor, these both operations can be done in log n time, or you may have said, I do a binary search for P on the study structure to find these two. So basically you need to write something there that indicates you use the study structure in a way that to have a log n processing time. If you use the entire study structure, I mean, it will be on for a point, and which will lead to on squared. So the entire study structure cannot be traversed. You have to make use of its balanced structure and perform operations only in log n time. So this was the solution sketch basically. The event queue, the study structure should be processed like this. Okay. Any questions about this solution? Yeah, I mean, I mostly you basically lost mostly 7 points if you do not give the detail of how you use the study structure. So there are lots of 93 grades. Many of you did the rest of the questions perfectly. So I mean, and 93 is a very good grade, I think. I mean, there will be lots of AAs from this course. I'm not going to do curve. if everybody gets good grades, I'm there. If half of the class gets all AAs, that's fine by me. Okay. So yeah, that was, I think that I mean, even with the small error, your exam was still very good. All right, let's continue with the other questions. I'm going to quickly go over the remaining ones. This part, second question, part A, and again, yeah, again, I actually, my wording for this question was not very good because I was asking for an efficient algorithm, but there were lots of solutions that gave the inefficient algorithm, which is so the efficient algorithm is, in order to look at the adjacent vertices of a given vertex, you could actually use the twin next origin records to walk over to traverse the edges that are incident on this vertex. But the brute force solution, which is very inefficient, is to go over the entire edge table and see where this vertex is associated with one of those edges, and use the origin or the target to report it. So if your edge table contains 1 million edges, the inefficient solution goes over all 1 million edges to report the incident adjacent vertices. So that's clearly very inefficient. But both of them got full credit because, again, I forgot to say here, give an efficient algorithm. So the dual graph, this question was real simple. Everybody got full credit. You just draw a polygon with a hole in it. When you draw the dual graph, you see that it contains a cycle. So therefore, it's not anything that has a cycle in it. It's not going to be a tree. So that was an easy question. And this third question, this is also very straightforward. Everybody got full credit from this also. So I'm going to skip this one. You just apply the algorithm in the book. Yeah, fourth question was not very easy, but you had to see the connection to the half space intersection problem. There were some hints in the question, like the expected running time being equal, expected linear time being linear. We have seen two randomized algorithms up to now, which are the 2D linear programming and the trapezoidal maps. Clearly, this is not a trapezoidal map algorithm. So this is not trapezoidal map, and therefore we are going to have the 2D linear program. So how come this be a linear programming algorithm? If you see that if the edges are like our linear constraints, then it's like the intersection of the interior of all of these edges will give us this. If it's non-empty, which is called the kernel of a polygon. If the kernel of a polygon exists, then it's called a star-shaped polygon actually. So we use the 2D linear program only to check for existence of intersection. So this is how the question was supposed to be answered. And this one, the solution to the question is already inside the question text. The number of points was a big hint. So in the internal nodes, we just store the count of leaf nodes for every subtree, and we accumulate these counts instead of reporting the entire subtree. The solution should be like that. Yeah. And if you wrote, for example, here, there were a couple of students who lost points here because they tried to store the entire subtree in the intermediate node, just like 2D range trees, which would make the space complexity n log n. It will increase the space complexity, and processing the nodes stored in the intermediate nodes, if you still process them in linear time, you will still have this plus k. So you would need a mechanism to actually accumulate the count of these. We don't need the actual members, we just need their count. So, and you can build this count during the building of the tree. And the final question, the trapezoidal map, again, it's very similar to the example in the book. So you just, the first two segments actually, it's the exact example in the book. And the third one is completely contained in the trapezoid here below. And what we have is, you can again use the example from the book for that. So this was how the exam questions, their solutions were. Okay, any questions on this? All right, let's continue with our regular lecture then. So what we have here is Voronoi diagrams, and if you look at the how we're doing in terms of schedule, there are 5 chapters left until the end of the semester, and we are going to have one free week at the end because I'm going to finish Voronoi diagrams today. And next week we are going to talk about chapter 8, arrangements and duality. It's going to be an interesting, nice problem. And we're going to see another data, 2 more data structures. Actually, there's another one inside this chapter which is not written, priority search trees, which are also known as trees, which is a binary search tree combined with a heap. So you'll see a data structure like that in this chapter too. And in robot motion planning, we're going to see Minkowski sums and finally visibility graphs. So these are the things that we'll see until the end of semester. So let's continue with Voronoi diagrams, what they are and how we compute it by using a plane sweep algorithm. So a Voronoi diagram, as I said, it's a subdivision of the plane. It's just, it has vertices, edges. Sometimes the edges may be infinitely long, and it has faces. Each point, which is a site in our input, has an associated face, has an associated area for it. It's called the Voronoi cell. These Voronoi cells, if you look at where the edges are, if you look at the vertices, the meaning of a Voronoi cell is that, as I said, it's the locus of points which are closest to that site. So for example, you take any point inside this face, that face will be closest to the site that is associated with the cell. So this site, all the points that are here, and since these are unbounded, all the points that are here, they are closest to this one. We can actually bound the Voronoi diagram. This is for practical reasons. This is what we usually do. We bound it in a bounding box that contains all of the vertices of the Voronoi diagram. The edges may be half lines. They may be unbounded, but if you want to see all of the vertices of the Voronoi diagram, we just put a bounding box around it so that all the vertices are inside. So they look very much like biological structures. If you look at a Voronoi diagram, it looks like an organization of cells, right? And that may be true because maybe this is what happens when cells try to grow. When cells try to grow in an environment, they start to influence each other. These edges are like the barriers between their influence points. This is, for example, the resources that are here, probably they can only belong to this nucleus that is right at the center. So it's like many biological structure, growth patterns, they resemble Voronoi diagrams. There may be other factors too that determine the shape of these. For example, if one side, if these are not points, if these are things with some strength, if this is, we may have weighted points. In that case, the influence area may look different. But in the simplest case, which we are going to see today, in the Voronoi diagram, we have points which are unweighted. They're all equal to each other. And the influence of these points around the space around them is just the plain Euclidean distance. So we will just that's the simplest form of Voronoi diagram. So we will just use the Euclidean distance and saying that given a point here, if it's Euclidean distance to all the points, if it's the smallest one is to this side, then this point belongs to the locus, the cell of this site. So that's how we are going to create our Voronoi diagrams. And if you look at this is a really interesting problem because if the input points, they are not part of the output. It's not like convex hulls or other structures that we have seen. In most of the things that we have seen up to now, the input point, somehow we use them either as vertices or it was part of they form the output. Here, if you look at the doubly connected edge list that determines the subdivision, it has vertices, edges, and faces. The points themselves, they do not appear in the doubly connected edge list directly. Maybe they can appear as an attribute of a face. For example, for a face, we can have an attribute saying that this is the center, not the center, but this is like the site of that Voronoi cell. This is the site of that face. We can have them as attributes, these input points. But other than that, the vertices, edges, or the faces of the Voronoi diagram, they are not directly, the sites are not contained in those records directly. So it's kind of an implicit structure that we are going to build. And if you look at the Voronoi diagram like this, the first part of this chapter talks about its properties. If you're given endpoints like this, how would a Voronoi diagram, how will a Voronoi diagram look like? How many faces we know it's going to have exactly n faces. If you're given n sites, n points, the Voronoi diagram will have n faces because we have a face, we have a cell for each site. Now, how many vertices or edges it's going to have? What's its complexity? Can it be quadratic, the number of edges or vertices? And how would the edges look like, or the vertices? What makes a vertex? Why is this a vertex, for example? Why is this an edge? Why do we have an edge at this position like this? Since we're talking about distances, these properties directly actually are derived from distances. For example, an edge of a Voronoi diagram is actually the bisector of 2 points. Bisector means that it's the line which is equidistant to 2 points. And the way you can derive the equation of this line is you can just have the line segment that connect these 2 sides, and the bisector will be exactly the orthogonal to this one. There will be 90 degrees. So if you just form the line equation that connect these 2, let me just copy this and try to talk about these things on our whiteboard. Okay, get me a new page. Oops. Didn't I go? Yeah. All right, if you take a look at this, flatten image. Okay, so the bisector is, you just connect these 2, form a line segment, and the slope of the bisector is 90 degrees from it. So if you know the direction from here to here is, for example, AB, the other is going to be B minus A. That's going to be the direction of the bisector. And we also know the point on the bisector, which is the middle point. The bisector passes through the middle of these points. So the middle point between these 2 things, if this one is V1, if this one is V2, the middle point will be V1 plus V2 divided by 2. So that's the middle point of these 2 points. So I have a line. You can form the bisector line easily with this equation. Let's call it the bisector as a parametric line. BT is equal to this plus, so this is, we can have this one as the origin, plus B minus A T. Okay, so this is the equation, parametric line equation of the bisector line. A line that passes through the middle point and has this direction, which is the vector that is orthogonal to our line segment. Okay, so this is going to be, this is how edges are formed. What about vertices? What's a vertex here? So on the edge, any point on the edge, is equidistant to V1 and V2. What about a vertex? It's like vertex is like an intersection of many edges. Like at this point, this is a vertex. Why? Because it's equidistant to at least three sides. A vertex will be a structure, a component of the Voronoi diagram in such a way that it's equidistant to at least three sides. So when a point is equidistant to three other points, some geometric shape comes into mind directly. So what is that geometric shape? So what can you draw around these things? A circle, right? A unique circle passes through three points, because here we are talking about distances and equidistant things. So we can put these 3 points on a circle, and this will be this distance, which is the same, will be the radius of that circle. And this is what a vortex is going to look like. And actually in the book, there are two lemmas, or there are properties about vortices and edges. A bisector, or a part of a bisector, will be an edge of the Voronoi diagram if the largest non-empty circle contains two sides on it. Which means that, for example, if you start with a point like this is not a side. We are just trying to see whether this is a point inside a Voronoi cell or on an edge or on a vertex. So we start growing a circle around it. And the first time we hit something, for example, the first time, so this is the largest non-empty circle. You hit some point, a site. If you hit a single site on this largest non-empty circle, what does this mean? It means that this point is inside a face. Okay? If the largest non-empty circle contains two sites on it, it means that this point must be on an edge. It's on the edge between these two things. If it has three or more, if the largest non-empty circle has three or more sites on it, so which means that the first time it becomes non-empty, there are three sites appearing simultaneously on it. It means that it's equidistant to all three of them, and it will be a vertex. Okay. The book also talks about the complexity of the Voronoi diagram, the number of vertices and the number of edges, and by using the Euler rule, the Euler theorem, that states that the number of faces plus the number of vertices minus the number of edges is equal to 2 in a connected planar. Did I write it correctly? Let me see. It may be incorrect. Actually, yeah, number of vertices, yeah, plus number of faces minus number of edges. I wrote it correctly. So yeah, number of vertices plus number of faces minus number of edges is equal to 2 in a connected planar graph. And these are a Voronoi diagram will be always connected, and it's planar, no edges intersect each other. So this property holds. We already know that this is equal to our number of sides. And if you look at each edge also has two vertices. Okay, there are no, there are two vertices around each edge. So we can also make use of that to get this into a single equation that's about the number of vertices, and this is what this one is doing, this theorem. And it's I'm just going to mention the result of the Voronoi diagram property. At the end, it's going to be linear. So for n sides, the number of vertices can be at most 2n minus 1, 5, and the number of edges can be at most 3n minus 6. So which means that the number of vertices and the number of edges can be linear at most. So the total complexity of the Voronoi diagram is linear. We don't have a quadratic complexity. And why do we talk about quadratic complexity? Let me just quickly now tell you about how can we compute the Voronoi diagram by brute force. What's this area that we see here for a certain site? This area that belongs to this site is actually, if you think about this, there's a single site around here. If there was only one other site, we would just draw the bisector, and this bisector will define two half planes, and the half plane that is closer on this side of this site is going to be the Voronoi cell of this thing, right? Now, if we focus on the Voronoi cell of this site S, when there is another site here, what will happen is that this other site is going to claim some of the points that belong to his. I mean, this one cannot claim. So this site can only claim the part that is closer to it. So due to this site, we know that if considering this site only, this center site is going to claim this half plane. But when we have an additional site, what it will do is it will say, okay, I'm going to get some of your area that belongs to you based on this bisector. This part belongs to me. So therefore, you can only have this part. So if you look at this, this really looks like a half plane intersection problem, and it is like that. So what we will do is, in order to compute the Voronoi cell, we can compute the intersection of half planes that are on the side of the center site. If you intersect those half planes, you will get your Voronoi cell for this S. So it's an intersection of half planes. So for a single site, we can compute the intersection of half planes in log n time using the divide and conquer algorithm in that 2D linear programming chapter. Because in this case, we really need the intersection. We cannot use the randomized incremental algorithm to find a single point on this intersection. We are not interested in whether the intersection exists or not. We actually know the intersection exists. For a site should always have a non-zero area face. So the intersection is going to exist. But we really need to find the shape, the actual intersection area. Therefore, we have to spend an O(n) log n time to do the half plane intersection problem using the divide and conquer algorithm. So if we do this for a single site, in order to compute the Voronoi diagrams of all the others, because we cannot make use of this when you're computing the others, because the intersection is with a pivot half space against the other. So when I'm computing the Voronoi diagram of this, the intersection is going to be with this one and the others. Okay, so so this will be like so I need to compute the intersection of these half planes for each of these sites separately, which will lead to an O(n) square log n algorithm. Because there are n sites, I compute the intersection of it with the others in n log n time. And then, so actually, let me show you. The book also mentions this as a property right here. Was it? Actually, it was in the property of the Voronoi diagram. It was the first property right here. So yeah, this is an observation. So the Voronoi diagram is for we are intersecting. It's the intersection of the half planes with pi, where pi is the center one. Okay, for each of those, we intersect actually. The bisectors are drawn with respect to the central site. So we'll have different bisectors for different sites. That's what we mean. For example, the bisector between these two sites, that half space do not appear when we are intersecting this. Okay, so the number of half spaces that we intersect is actually not n. There are n square, because there are n square pairs of sites. There are n square half planes, but we do not. So that's why we have this n square log n complexity. the bisector between these two sites, which is this one, this half space, is not considered when we're finding the area for the central site. So this is the brute force algorithm, and we are going to reduce this to O(n) log n with Fortune's algorithm. So in n log n time, we are going to find the entire Voronoi diagram for all of the sites. Okay, but the brute force could be employed. If you're not considering efficiency, you may use an existing algorithm for half space intersection to compute the Voronoi diagram. All right. Now we have talked about, so this figure here also talks about what's an edge. As you can see, a point on the space will be part of an edge if the largest non-empty circle contains two sides, exactly two sides. If it has more than three or more sides on it, it will be a vortex, the largest non-empty circle. So these observations will actually lead us to our algorithm. We will make use of these things. And our plane sweep algorithm is going to create the Voronoi diagram. As we move the plane sweep downwards or from left to right, we will create it as a doubly connected edge list with vertex, edge, and face information. And yeah, this is now here's the next thing is we're going to look at this interesting thing. Why do we have what does this figure say? Let's take a look at that. So here, this figure is talking about how with a sweep line we can compute the Voronoi diagram. But usually in a plane sweep algorithm, what we have is everything above the sweep line, we are moving downwards. Above the sweep line, we know everything about the problem, and below the sweep line, we haven't yet processed any event points, and we don't know anything below the sweep line. And the sweep line is opaque to us. We cannot look ahead and ask for things because that will increase the computational complexity. If your algorithm tries to do something that is related to what's beyond the sweep line, it may increase the complexity. We just need to localize our problem with this plane sweep. Whatever the current event point is, we process that, and based on that, and based on all the other events that are processed before, we have some solution for the part above the sweep line. Below the sweep line, those events have not been processed yet, and we don't know anything. So in this figure, the dashed lines show the Voronoi diagram actually that is not known to us yet. We don't know it yet. And the solid lines show the part of the Voronoi diagram that we know for sure. Okay. Now, the interesting thing here in this plane sweep algorithm is that there are some parts above the sweep line that we may not know. That's what makes this interesting. And unlike other plane sweep algorithms, we don't know everything above for the part above the sweep line. Some parts are not known. And why do we have these parabolic shapes that marks the boundary between the known and the unknown? Why is this place, a point here, is not known to be part of this Voronoi cell? Because there may be an event point just below the sweep line that may claim certain places from this cell. We cannot say that everything that's above the sweep line is belong to this cell. We cannot do that because there may be a point right below the sweep line, and that point will be shorter distance to this previously processed event point that is a certain distance above the sweep line. In other words, we need to look at something like this. If this is the sweep line, and if this was a site that we have processed earlier, for a point, let's look at a point here. Can we say this point belongs to the site cell? We don't know. Actually, we cannot say that because if there was a site right here underneath the sweep line, that will actually make this P to belong to this one. So what are the boundary points which we can say that be above the boundary all the points are guaranteed to belong to this Voronoi cell of this side, and below the line we don't know anything. We cannot say it's guaranteed to belong to the other one. We just say we don't know. Below the boundary we don't know anything. So if you look at a point in the boundary, let's look at a point in the boundary, what we are actually comparing is this: the distance of this point to the sweep line is simply given as the y coordinate of that point, whatever it is, minus the y coordinate of the sweep line is the distance, right? We are comparing this distance with this distance. And the place where these two distances are equal to each other is defining our boundary. And the boundaries actually are dynamic. It's going to change. This parabola, the shape of this parabola is going to change as we move the sweep line downwards, right? Because this Ly changes. Ly changes, and therefore the boundary is going to change. So let's try to look at the equation of these arbitrary points. All the points along this parabola satisfy this equation actually. If this is my site, the distance between this point and the site, which is like px minus sx squared plus py minus sy squared. So this is the distance of that point to the site, and this is the distance of that point to the sweep line. When these two are equal, we get ourselves this equation. And this equation is going to turn out to be, if you just take py, if you try to write py in terms of px, so you can arrange this line for this equation. For example, take the square of both sides, okay? It's going to be py squared minus 2py ly plus ly squared. Okay, this is the left hand side, and the right hand side is going to be just take the square of this thing, px squared minus 2px sx plus sx squared and plus py squared minus 2py sy plus sy squared. Okay, so I just take the square of both sides and I open these parentheses squares. Okay, now what is interesting here is that look at these two py squares. They cancel out. Okay, in other words, when we are trying to write py in terms of py, there is no py square term here. Okay, so there's py, this ly square, it's a constant. Sy square is a constant. These are constants. Okay, we know the coordinate of s, we know where the sweep line is, so these are our constants. And what will happen is that there are some there are some px square terms, px terms, and there are some constant terms. In other words, it will be like an equation like this. Any point, it will be like y is equal to ax squared plus bx plus c. So it will be an equation of a geometric object that looks like this. And what is this? A parabola. Okay, so this is an equation of a, by changing these ABCs, you are going to get yourselves a parabola. Okay, so here's so what it tells us that our boundary between the known part of the Voronoi diagram and unknown part of the Voronoi diagram is no longer the sweep line itself. The sweep line's position is important, but the boundary between known and unknown part is actually a sequence of parabolas. Each of these parabolas, they belong to different sites. There will not be a single parabola. This is called the beachfront. These are like waves that are coming on the shore on a beach. So this is called the wavefront or the beachfront. And these are like breakpoints between waves. When waves touch each other, so they break, and these are like breakpoints between the waves. And this is how we are going to have our study structure. Our study structure will be a sequence of parabolas above the sweep line. And one thing that is interesting is that this is an X monotone beachfront, meaning that any vertical line intersects the beachfront at a single point. So it's like a curve that moves always to the right. Okay, it's not going to go left. It's a vertical line will not intersect this beachfront at more than 2 points. So we can have, and we can represent this as a sequence of parabolas from left to right. And we are going to maintain, this is going to be our study structure, and we will handle these event points. But there will be site events, and there will be some also interesting events that I'm going to show. But before we start the details of the algorithm, let's have a 10-minute break, let's have a 10-minute break. And 10:41, I'm going to continue with this plane sweep algorithm and talk more about. I talked about site event. We will see something like these vertices will be interesting. We will mention something like circle events, but I'll do the details after the break. So yeah, 10:42. I will continue the lecture at 10:42. I'm stopping the recording right now.